In this video, we are going to talk about work, heat, and how these are related to the first law of thermodynamics. So what we will be talking about in this video are what are called reversible processes. To make a process reversible, we must change the volume very slowly, what is known as quasi-static. This is usually thought of as doing an infinitesimal change in volume, so dV here, then letting the system come to equilibrium, which we haven't really formally defined yet, but if you just think about it intuitively, so we're letting it come to equilibrium before doing another infinitesimal change in volume, and so on. So you do this multiple times, adding up to a finite change in volume. This is so we avoid dissipative losses, so losing energy through friction and things like that. And therefore the magnitude of work performed by or on the system is maximized. When not doing it this way, the process is said to be irreversible. Many thermodynamic ideas are based on the systems that undergo reversible processes. For a gas, a reversible change is one where the internal pressure is at all times equal to the external pressure. So we always want that the P external is equal to the P internal. And so we can make a substitution in our equation for work. So this is the equation for work we've derived in the previous video. And so we want to make a substitution for this P external here to determine that the pressure volume work for a process in terms of the internal pressure. So since we know these are always equal, we just put the pressure for the internal, so the system pressure, into our equation there. Then we can use the ideal gas law to substitute in for the internal pressure. So we know if we solve for the internal pressure in our ideal gas law, we get this. So we just put this nRT over V into our equation, and so we end up with this right here. If we assume the process is isothermal, meaning that the temperature will not change, we can bring all those constant outside the integral. Then we solve the integral, where we have the 1 over V right here. That just becomes the natural log of V. Then evaluating it at the limits, so our V initial and V final. So what we end up with is this right here. So we have the ln of V final minus the ln of V initial. Using this logarithm rule, where we then end up with ln of V final over V initial, we get this right here. So this is our work expression right here. Using Boyle's law, so that's the Pi Vi equals Pf Vf. So these are our final conditions. These are our initial conditions. We can make this substitution right here, where Vf over Vi can be substituted in for Pi over Pf. So notice that now the initial is on top and the final is on bottom. So in terms of pressure, the expression becomes this right here. If we look at an example for this, say we have gas in a piston chamber kept at a constant temperature bath of 25 degrees Celsius. So a constant temperature bath just means that the temperature is not going to change inside the piston. And it expands from 25 milliliters to 75 milliliters very slowly, so reversibly. If there is 0.00100 moles of ideal gas in the chamber, we want to calculate the amount of work done by the system. So this is what's shown right here. We start with 25 milliliters. We'll let this expand out slowly so that then we end up with 75 milliliters total inside the gas chamber of our piston. So what we do is just plug in these numbers into our equation. So this is our number of moles right here. This is our gas constant right here. This is our temperature. Then we have the ln of our final volume divided by the initial volume. When we calculate this out, we see that we end up with minus 2.72 joules, meaning that 2.72 joules is lost by the system. So remember, we're always looking at this in the point of view of the system. So this negative sign tells us that the system is losing the energy. If we do this specifically for 0.00100 moles of this sulfur dioxide, we can then use the van der Waals equation. So these are our van der Waals constants right here for it. We then put this into this van der Waals equation. We get it in terms of the pressure. We substitute that into our work formula. We go through a bunch of math here, but what we end up with is that the work is equal to minus 2.71 joules. So remember, when we assumed an ideal gas, it was minus 2.72 joules. For the real gas, it's minus 2.71 joules. So not that far off, but we're still, again, losing energy from the system. Heat, which is represented by Q, also has units of joules, so it is a type of energy, is measured using temperature. When heat goes into a system, the temperature increases. When heat leaves the system, the temperature decreases. for the same change in temperature, different amounts of heat are required for different materials. For instance, if we have 10 cubic centimeters of iron, this requires less heat to raise the temperature by 1 degree Celsius than does 10 cubic centimeters of water. The amount of heat necessary to raise some material by 1 degree Celsius, for instance, is proportional to the amount of mass and the change in temperature. We will find that for some given mass of a substance, which we'll call m sub here, the ratio of heat to mass times change in temperature is some substance-dependent constant, and so we'll just call that C right here. So in other words, if we take the heat, divide it by the mass times the change in temperature, that will give us this constant right here, and this is going to be substance-dependent. This proportionality constant for a given substance is called the specific heat of the substance. What it tells us is that materials with low C require less energy to raise the temperature. So for instance, metals, which is often somewhere between 0 and 1, we can look at that in the table to the right here. We see that for our metals, like copper or iron, that these are between 0 and 1. While a high C requires more energy to raise the temperature. So for instance, liquid water has a C of 4.184, and the units on that will be joules over gram degree Celsius, which is how we define what the calorie is. So 1 calorie equals 4.184 joules. While specific heat is an intensive property, we can also use the extensive property called the heat capacity, which is represented with the uppercase C and has units of joules per Kelvin. And so we would use this right here. Both work and heat are types of energy. They both have units of joules, but what differentiates them is that work is directed. So if we look over here, the work is just all these molecules moving in the same direction, and thus can apply a force over some distance in that direction, while heat is random. So in heat, these particles are all just moving in random directions. So you'd not be able to get any sort of useful work out of that, because any work that, say, this particle does would just be canceled out by the work that this particle does. And so you end up with just randomness for it. So those are heat and work. The total energy of the system is the internal energy, which I will hereafter denote as this E sub cis right here, since U in later videos will be used for potential energy as we go forward. This is the energy from different sources, such as chemical, electronic, nuclear, though in thermodynamics we're often not really interested in nuclear energy, and kinetic energies, although we ignore energy coming from the movement of the system's entire reference frame. What I mean by that is if you think about the movement of the air coming along with you in your car as you drive. Recall that closed systems do not allow for matter to move in or out of the system, while isolated systems do not allow matter or energy to move in or out of the system. We can state the first law of thermodynamics this way. For an isolated system, the total energy of the system remains constant. Energy within the system, which we'll just call this E isolated system, can change forms, but the amount of energy within the system remains the same. The mathematical way of writing this would be this, so the change in energy is always equal to 0. If the universe is considered an isolated system, which it often is, then we derive the popular notion that matter and energy can never be created nor destroyed, and that would apply to the entire universe. However, in thermodynamics, we are not usually talking about isolated systems. We are interested in studying systems that can transfer energy with the surroundings. In engineering, for instance, we are often concerned with how much work that we can get out of a system and how much of the energy is wasted as heat. We thus think of the change in internal energy of a system as the transfer of heat and work, and in particular as the transfer of heat and work with the surroundings. This equation could then be considered another expression of the first law of thermodynamics, which says that for a closed system that is not isolated, meaning it can transfer heat with the surroundings, the change in energy of the system is done through the transfer of heat and work with its surroundings. So for instance, something like this, where we have more energy coming in than going out, then the Q would be positive, where here if we have more work going out than coming in, the work would be negative. And so all we're doing is transferring heat and work with these surroundings. As an example, consider a sample of gas that undergoes a reversible change in volume from 4 liters to 6 liters against an external pressure of 1.5 atmospheres and simultaneously absorbs 1,000 joules of heat. So that's what this looks like here. So we have heat coming in, we have work going out, we have a pressure at time 1 T1 of 1.5 atmospheres and a volume of 4 liters. Then we have some temperature T1. After we lose energy through work, gain it through heat, we end up, again, because this is reversible, the pressure stays the same and the volume increases, and the temperature at time T2 would be greater than the temperature at time T1. And the increase in temperature would be based on this, where we have the change in internal energy for the system over the amount of stuff times the specific heat of the gas that's inside of it. We can calculate the change in internal energy by first calculating the work, so we just put that into our work equation here for this change in volume, which is going to be the 6 liters minus 4 liters. Then this is just to convert it into joules out of the liter atmospheres here. And so we end up with work being minus 304 joules, meaning that the system is losing 304 joules by doing this work. And then because we stipulated that we're increasing the heat by 1,000 joules, we get that the net change in internal energy is this. So it's just the Q plus W, so the 1,000 joules plus the negative 304 joules. So the change in internal energy is 696 joules. Thus, the internal energy of the system has undergone a net increase of plus 696 joules, which in a closed system, meaning that the amount of stuff is not changing, and at constant pressure because it is reversible, this can only occur if we have this increase in temperature. An adiabatic system is one in which, by definition, so we're just stipulating this, the flow of heat is equal to 0, so it is neither gaining nor losing any heat. And so then we would just use this for the change in internal energy. Again, we will talk more about this in future videos. But anyway, that was everything I wanted to talk about in this video. I hope you found that helpful, and I will see you in the next one.